Welcome to the next video on discrete mathematics. This is video 6, where we'll discuss the proof that this function j of n, which is the function introduced in the previous video, has the hypothesized formula 2l plus 1. This corresponds to chapter 1, section 3. So let's recall all of the setup here. If we take any given n, we said that we would decompose it into a portion which is the largest exponent of 2 that is less than or equal to n, and whatever remains, which would be L here. So L will always be taken between 0 and 2 to the m. Now we're going to prove by induction that this satisfies the following formula. Let's also recall all the collected facts about the function j. So we know that at 1 it is equal to 1. We discovered two recurrence relations, one for even terms, and one for odd. Now, because there's an even and an odd, then normal induction is not going to work. Also because things sort of proceed by going by halves, or by doubling in whichever direction you want to think about this running in. But in any case, it's not, it's not one thing after another, right? Things are kind of skipping by twos in a sense. Well, in a situation like this, we can use the same logic of induction. Recall what the logic of induction is. If you want to prove that something is true for cases 1, 2, 3, 4, 5, and so on, then you first prove that it is true for the first base case, and then you prove a kind of conditional principle that if it is ever true for one thing, it must be true also for the next, right? And so if you get to do that over and over again, right, since it is true for one, it must be true for two. But by the same sort of conditional principle, since it is true for 2, it must also be true for 3, and so on. So then you get that it is true for everything. Well, here we're going to apply a similar logic. It just doesn't go in a straight line. It branches, right? From 1, right, again, we're going to have 1 as a base case. That doesn't change. But from 1, we can get to 2 by talking about, sort of not by plus 1ing, whatever case we're at, but by times 2. And we can also get to 3 by kind of the same thing, except taking times 2 plus 1, right? So we can get from 1 to 2 and 3 using a sort of conditional principle, where this time rather than using plus 1, we use times 2. And we can get from 1 to 3 by using a conditional principle for going from any case n to 2n plus 1. And then from 2, we can get to 4 and 5, right? So again, using the same conditional principle for times 2, we get to 4, and using the conditional principle for times 2 and times 2 plus 1, we get to 5. And then using these same principles, but this time from 3, we get to 6 and 7, and so on. We can reach every possible number along this branching tree by following some sequence of either times 2 or times 2 plus 1. So that's going to be the nature of how we do the induction in this situation. Now, the proof of the base case is, as usual, pretty straightforward. So we're going to start from n equal to 1. We're going to look at, right, we're trying to claim that j of n in this particular case, that's j of 1, and we compute that that's equal to 1. We're trying to prove that it's given by the same thing as this formula, 2l plus 1. Now, to compute 2l plus 1, we first have to find the largest power of 2, which is less than or equal to the given number. Well, the given number is 1, and the largest power of 2 less than or equal to 1 is 2 to the 0. So that determines that m is equal to 0. L makes up the difference, so L here is 0 in that case, because 2 to the 0 just is 1. So we've determined that L is 0, and now when we evaluate the formula 2L plus 1, it evaluates to 1. Since these two values match, then that confirms the base case. Now let's move on to the inductive case. So we're going to suppose that n is something greater than or equal to 1. We'll assume that it has a decomposition into a 2 to the m plus L here. As always, L taken from 0 inclusive to 2 to the m exclusive. And we will assume that the formula holds for n. We're then going to prove that it must also hold when applied to 2n. Now, part of this is rather straightforward. We're going to simply expand the formula and then use what we know from the inductive hypothesis about j of n, simplify things so that it becomes 4L minus 1. Okay, but we have to maybe be a little extra careful when we look at the other side of this, because when we're talking about 2n, the value of L is not the same, right? We need to find the lowest exponent of 2, which is less than or equal to 2n this time. It doesn't take much work to demonstrate that if 2 to the m, right, if m is the least exponent of 2 less than or equal to n, then 2 to the m, right, is going to be the least exponent of 2, which is less than or equal to 2 to the 2n. So this is our new 2 to the m, so to speak, or 2 to the m plus 1. And so it may determine a new L prime. So we're going to say that 2n is 2 to the m plus 1 plus L prime, right? L prime is going to make up the difference between whatever this power of 2 is and 2n. Now the question is, what is L prime? Especially, how can we relate it to this? So we'd like a relationship between L prime and L. So if we write down 2n, let's use something else, right? We know this about it, but let's write something else which we know about it, namely that we were already using the 2 to the m plus L to represent n. So I can simply replace n in that way. Distribute, so I get 2 to the m plus 1 plus 2L. Now we already said that all of this is equal to 2 to the m plus 1 plus L prime. Well, if you now cancel the 2 to the m plus 1s, and then you get this equation that 2L equals L prime, and that's exactly what we needed to be able to conclude the proof, right? So we can now return to what we said before, that j of 2n is equal to 4L minus 1. But if it's equal to 4L minus 1, and we have this equation 2L equals L prime, then 4L minus 1 becomes 2L prime minus 1, and this is exactly the formula that we needed for the case 2n. So I'm not going to trace through the demonstration for the 2n plus 1 branch. It goes very similarly. I'll leave that as an exercise, but leave a comment if that causes any problems, and I might be able to resolve any confusion there. But I'm going to regard that as proof complete. If you appreciated this content, please like and subscribe. And if there's anything that we discussed here where you'd like to see it elaborated further, I might be able to answer questions in the comments, or for substantial topics, I might make an entire video and add it to the playlist.